Um, Next example I want to show you, because I mentioned at the beginning of this video that we use complex numbers a lot to solve real problems, even though complex numbers, they involve imaginary numbers that don't physically exist. We can use it as a means and as a tool to quite elegantly solve a lot of real problems. And here's the first example of that. So what I want to do, I want to use complex numbers to prove the parallelogram law, which at first glance has nothing to do with complex numbers. It's just one of the features of parallelograms. So what we know about parallelograms is that if you take the sides and you square them, if you square their lengths and you add them up, right? This is the same as adding the squares of the lengths of its two diagonals. And this is called the parallelogram law. And I'm going to show you how to prove it using complex numbers. So, let me first draw my Argand diagram again. So I need to form a parallelogram using complex numbers. And I think you can see how I'm going to do that based on the previous example. So let's say if this represents Z and this represents W. So let's say I call this Z and I call this W. So I mentioned that when you add Z and W, it works like vector addition. So Z plus W would be here. And so I got a parallelogram happening. So this guy is parallel to this guy, and this guy is parallel to this guy. Okay, now the length of this edge is obviously modulus of Z. And the length of this edge is obviously modulus of W. Because modulus just means distance from the origin. And if you think about it, because it's a parallelogram, the length of this side is the same as the length of this side. And the length of this side is the same as the length of this side. So when we say the sum of the squares of the lengths of the four sides of a parallelogram, it's just going to be 2 times mod Z squared plus modulus of W squared. Right? And this should equal the sum of the squares of the lengths of its two diagonals. So we got two diagonals. The first diagonal is this, going from here to here. The length of this one, because it's the distance from the origin to Z plus W, the length of this one is just modulus of Z plus W. Now the other diagonal that we have is going from here to here, and based on what we just said in the previous example, we know that the length of this one is modulus of Z minus W, because that diagonal is basically the length from Z to W. So what I want to show that this equals Z plus W squared plus modulus of Z minus W squared. So you can see I've taken the problem and I've kind of written it in the setting of complex numbers. And now using the properties we spoke about before, I'm going to use complex numbers to prove this. So let's have a look at the right hand side. Right? Now I got modulus squared plus modulus squared. Remember, before we said that if you take a complex number and if you multiply it by its conjugate, you get the modulus squared. So I mentioned that if you have like a complex number alpha and you multiply it by its conjugate, you get the modulus of alpha squared. This is the idea that I'm going to use here. So instead of saying the modulus of Z plus W squared, I'm going to say this is the same as saying Z plus W times the conjugate of Z plus W. And likewise the second guy, I can think of it like this. Z minus W conjugate, right? And one of the other properties that we also spoke about is that instead of adding and then taking the conjugate, you can take the conjugate and then add, or subtract for that matter. So using that property, I can split up the conjugate like this. And now what I do is I just expand brackets. So if I expand the first bracket, ZZ conjugate plus ZW conjugate plus WZ conjugate plus WW conjugate. That was the first couple. Then if I expand the second couple brackets, right, I get ZZ conjugate minus ZW conjugate minus WZ conjugate plus WW conjugate. And you can see that some nice cancellation occurs. So the ZW conjugates cancel out, and the WZ conjugates cancel out as well. And so what I got 2 lots of ZZ conjugate plus 2 lots of WW conjugate. But remember, when you multiply something by its conjugate, you get the modulus squared. And this is exactly the left-hand side. So you can see it's a very slick way, and a very nice way, I reckon, of proving the parallelogram law. But again, the parallelogram law, that's a purely real problem, right? Parallelogram is a real thing, and this is a real property. But I proved that using complex numbers. And this is kind of the idea that I was referring to before. Complex numbers, they provide a means to very elegantly prove a lot of real problems. This was just a very small example to give you an idea, but this idea is rampant all throughout mathematics. So that's why one of the reasons why complex numbers are so useful. Okay, so we've spoken now. Hopefully now you're comfortable with the meaning of modulus and argument. I want to talk a little bit about the properties of the modulus and argument, so some important properties that you need to know. So here's a little list of the most important ones. So the first dot point is saying that the modulus of z times w is the same as saying the modulus of z times the modulus of w. And we also know that the argument of zw is the same as the argument of z plus the argument of w. So really what that's saying, it's saying that when you multiply two complex numbers, in terms of their modulus, you're multiplying their lengths as well. But when you multiply two complex numbers, in terms of what you're doing to their angles, you're actually adding their angles. You're adding the argument. So let me show you why that's true. I'll prove the first one for you. It'll be a really good idea if you try to prove the remaining ones as well as a useful exercise. So in fact, I should have mentioned it earlier and I forgot, but with all the exercises that I'm doing in this video, probably the best thing you could do to help your learning is, before you watch me do the example, pause the video, try to do it yourself, and then watch me do it. That's the best way to learn. It'll be much more efficient and effective if you give it a try and then watch me do it rather than just watch me do it. So just keep that in mind going forward. So let's try to prove this first bullet point. Okay, so in order to do this, we'll just take two random complex numbers. Of course, we'll take two random complex numbers in polar form because we're interested in their properties of modulus and argument. So let Z be, let's say, R1 cos theta 1 plus I sine theta 1. And let's say W is R2 cos theta 2 plus I sine theta 2. Okay. Have a look and see what happens when we multiply these two complex numbers. So when you multiply Z and W, obviously you get R1, R2. And then you get the product of these two brackets. Okay, so now if you expand these brackets, you're going to get cos theta 1, cos theta 2. You're going to get I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2. And the final term that you're going to get I squared sine theta 1, sine theta 2. But remember, I squared is negative 1. So that really just becomes minus sine theta 1, sine theta 2. Okay, and what happens next? I'm going to group it like this, cos theta 1, cos theta 2. So I'm going to group the real terms together and the imaginary terms together. Like that. Now notice something interesting happens, right? We know from our trig identities that this is the same as saying cos theta 1 plus theta 2, right? This is using the trig identities you learned in high school. And we know that this is the same as saying sine theta 1 plus theta 2. So in fact, what I found that I get R1, R2, and then cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So the product is a complex number, and when I write in polar form, the modulus is R1, R2, and the angle, the argument is theta 1 plus theta 2. So in other words, I can see now that the modulus of ZW is R1, R2. But remember, R1 is the modulus of Z, and R2 is the modulus of W. Likewise, I can also see that the argument of ZW is theta 1 plus theta 2. Where remember, theta 1 was the argument of Z, and theta 2 was the argument of W. So this shows that when you multiply two complex numbers, right, you add their argument, but you multiply their modulus, right? And that's what the first property is showing. So we've proven that one. So the second dot point is similar, and I suggest you try to prove it yourself. So it's basically saying when you divide two complex numbers, you divide their modulus and you subtract their argument. Okay, the third one is an important property as well, and that one's very straightforward to see. So the modulus of Z and its conjugate are the same. So it's easy to see why that's true, because remember, when you take the conjugate, you're flipping a complex number, you're reflecting it about the horizontal axis, so you still have the same length from the origin. Or if you want to see it a bit more explicitly, you can say, okay, if Z is R cos theta plus I sine theta, right? The conjugate is just R cos theta minus I sine theta. So in both cases, they got the same modulus, R. So that one's fairly easy to see, but important to remember. Okay, let's do an example just to get used to these properties. So I got this example here. So I got a complex number Z, a complex number W, and I want to calculate their product and their quotient using those properties. So for part A, remember that when we multiply two complex numbers, we multiply their modulus. So the modulus of the first one is 6, modulus of the second is 2, 6 times 2 is 12. Now the argument of the first complex number is pi on 4, the argument of the second is pi on 3. When we add these two, we get 7 pi on 12. So therefore, the product is going to have a modulus of 12 and an argument of 7 pi on 12. And that's pretty much it. So when you know those properties, it becomes easy to multiply complex numbers in polar form. Likewise with part B, again, we divide the modulus, so 6 divided by 2 is 3. And when we divide, we have to subtract the argument. So we do pi on 4 minus pi on 3, and that gives us minus pi on 12. So therefore Z on W, that's the complex number that has a modulus of 3, and the angle is minus pi on 12 plus I sine minus pi on 12, like that. So perhaps you're wondering, well, how will we write this in Cartesian form? Certainly in the case of pi on 12, evaluating cos and sine is not so easy because we can't just use our exact triangles. Our exact triangles are there for pi on 3, pi on 4, pi on 6, angles like that. So if you want to evaluate these, you just have to do some trigonometry. You just have to use your double angle formulas. So for example, in the case of 7 pi on 12, right, if you want to evaluate cos and sine of that guy, you have to use, or you can use this identity here, cos 2 theta equals 2 cos squared theta minus 1. So I take 7 pi on 12, and I try to write it in terms of an angle that I do know how to evaluate. In this case, 7 pi on 6. So if I let theta to be 7 pi on 12, then 2 theta is 7 pi on 6, so I get cos 7 pi on 6 equals 2 cos squared 7 pi on 12 minus 1. Now, like I said, I know, and you guys should know, how to calculate cos 7 pi on 6. So once I do that, I can make cos 7 pi on 12 the subject, and solve cos 7, and then evaluate cos 7 pi on 12. So I can get this guy. And then I can also easily get sine 7 pi on 12, because I know that sine squared 7 pi on 12 plus cos squared 7 pi on 12 is equal to 1. So if I know what cos 7 pi on 12 is, I can solve for sine 7 pi on 12 and go from there. So obviously it's a bit of work, but at the same time it's also straightforward, right? There is a systematic way to do it.